Good morning, life science students. How are you all? Today we will be discussing saponification part 3, which concludes the saponification lesson. Let's discuss the solubility of soap. Number 1, the solubility of soap in pure water or distilled water. Soap, ladies and gentlemen, is slightly soluble in pure water or distilled water. And anytime you see a state of equilibrium between the soap, which is represented by RCOO and you have its ions on the right, RCOO- plus Na plus, remember that the RCOO- is indeed the soap molecule or the soap ion. So anytime we have a state of equilibrium, this means that this reaction is not complete, it is incomplete, therefore the soap is said to be slightly soluble in distilled water. Number 2, hard water. What is hard water to begin with? Hard water is the water that contains high quantities of calcium and magnesium ions. Soap is insoluble in hard water. And the equation shows why the soap is insoluble in hard water. You have the calcium ion that is present in hard water reacting with two molecules of aqueous soap to produce RCOO2Ca in the solid state plus 2 Na plus. Anytime you have the soap in the solid state, this means that the soap is insoluble. Therefore, soap is insoluble in hard water simply because the aqueous soap is simply converted into a solid form of the soap. Therefore, it is classified as insoluble. Now, in acidic medium, the soap is also insoluble. Again, looking at the equation, the RCOO- is the soap molecule, or the ion, doesn't matter, plus the H2O+, which represents the strong acid, producing RCOOHS, which represents solid, plus H2O. Since we converted the aqueous soap into a solid form of the soap, therefore the soap is insoluble. Now, in a solution containing Na plus ions, soap is also insoluble. Looking at this equation right here, we have RCOO, which is the soap molecule, in equilibrium producing RCOO- plus Na plus. Now, increasing the amount of Na plus causes the equilibrium to shift backwards towards the precipitation of the soap. And what is meant by precipitation of the soap? It means that the soap is in the solid state. This process in chemistry is called the flocculation or relargage, which separates the soap from other substances found in the container where the preparation of soap is taking place. You will see this information later in upcoming slides. Preparation of soap in lab. Step number 1. Guys, in order to prepare soap in lab, the process is done by heating by reflux. And the heating by reflux was discussed earlier in previous slides and previous videos. Now, in lab, we use ethanol in the reaction system. Remember that the reaction system in the saponification process is the triglyceride, which is oil, and the strong base, like sodium hydroxide or potassium hydroxide. Now, since the base and the oil are immiscible liquids mean that those two liquids do not mix together. Ethanol is miscible with both. So the use of ethanol along with the triglyceride or the oil and the strong base increases the surface contact between the oil and the base, since, like mentioned, ethanol is miscible with both. Now, when you increase the surface contact between the oil and the base, This increases the yield of the reaction. Heating in this process increases the rate of this slow reaction. Remember when we talked about the characteristics of saponification, we said that the saponification reaction is slow and complete. So think about it here for just one moment. Increasing the heat or simply increasing the temperature. Temperature is a great kinetic factor. As temperature increases, the rate of the slow reaction also increases. From step 1, the produced soap is in the aqueous form. Now, in order to collect the soap, we need to flocculate the soap, or in other words, we need to simply convert the aqueous soap into the solid form of the soap. This is step 2, called the flocculation. Now, flocculation is the addition of aqueous salt solution which contains Na+ and Cl-. Now, remember that in the beaker we have the soap in the aqueous form. So we have RcOO- and Na+. Now when you add large amount of Na+, what happens to the equilibrium? The equilibrium will start to shift backwards towards the precipitation or the flocculation of the soap molecules. So the addition of aqueous salt solution, which is Na+ Cl-, causes the soap to flocculate or solidify and float on top of the solution that is left behind. Now the solution that is left behind contains leftover Na+, leftover OH- from the strong base, and of course you got Cl- from the NaCl, and we have a glycerol left behind, and water, and also ethanol. Remember that the soap is insoluble in aqueous salty solution. This causes the soap to separate from the solution and flocculate. So ladies and gentlemen, in order to flocculate or solidify the aqueous soap that we have in solution, we need to add a very substantial amount of sodium chloride solution, which causes the equilibrium to shift from the right towards the left towards the production of the solid soap. Remember, the solid soap is RcOO- or RcOO-. Once we have that done, then the soap can simply be separated from every single constituent we have in the left behind solution. Now let me just recap what is left behind in the solution after the soap simply floats on top. We have leftover Na+, leftover OH-, leftover Cl-, glycerol, water, and ethanol. Now step 3 is the filtration process, which concludes the steps of the preparation of the saponification in laboratory. This process is carried out to just simply collect the soap and dry it out by using the vacuum filtration. The vacuum filtration is the process by which we can speed up the filtration process so that the flocculated or the solidified soap can be collected on the filter paper, and of course the left behind solution, which is the filtrate, will simply be collected in the Erlenmeyer flask. This, ladies and gentlemen, concludes the saponification unit. Until next time you hear something from me, love you all and God bless.